name is Luna Phipps-Costin. I'm an undergrad at UMass. This is joint work with Carolyn Jane Anderson at Wellesley, Michael Greenberg at Stevens, and Arjun Guha at Northeastern. In the past, programmers have had to choose between statically and dynamically typed languages. However, in the last couple of years, gradual typing has seen an increase in popularity, which allows programmers to mix statically typed and dynamically typed code in the same program. A number of dynamic languages have gradual type systems for them. However, adding types to dynamic code can be a long and difficult process. And many programmers introduce errors into their type annotations. Christensen and Muller found errors in a number of popular TypeScript type declarations. So we're interested in automatic gradual type migration, not for any of these languages, but for a research language we were working on. And we looked at prior work in the space. All of these works work on the gradually typed lambda calculus, which is a standard typed lambda calculus, except that it has an any type, which is compatible with all other types. So if we can use an ML-like notation here, we can write something like this funny function here that uses b only as a Boolean to decide whether to use x as an integer or as a Boolean. So a human annotator should be able to say that b should have type Boolean, and x should keep its type of any because it's used in a dynamic way. However, if we look at what these tools do to migrate programs, even on the same program, they might not give the same migration. This is because they prioritize different properties. So we have to ask which properties matter for automatic type migration. The first property that matters is precision. So if we want to talk about precision, let's talk about this function. It accepts a function, it applies it to true, and it applies the function to that result. So we can improve the annotation on G to be any arrow any because it's only used as a function. We can also further improve that annotation to Boolean arrow Boolean, and there's no further improvement possible here because there's no any types to improve. However, in doing so, we may have restricted the number of contexts in which the program can be used. The second property that matters is compatibility. So the original program can be applied to a constant function that returns 10 and will behave as expected. The result will be 10. When we improve the annotation to any arrow any, we get the same result. However, when we improved it to Boolean arrow Boolean, we'll see a static type error because the constant function has the return type of int, but the annotation has the return type of Boolean, and so they're inconsistent. So we can see that whenever we improve precision, we may be sacrificing compatibility and restricting the number of contexts in which our program can be used. The third property that matters is safety. So if we have a function that accepts an identity function and uses it in two ways, with ID true and ID true, with two different types, and then apply that function to an actual identity function, we might be able to improve the precision of this as any arrow any because the identity function is used as a function. You might think that's the best we can do without polymorphism, but we can actually improve the precision of the argument annotation on the identity function and say that it's a Boolean. And this will actually type check because Boolean is consistent with the any annotation, and the application ID2, the integer, is also consistent with the any. So this non-transitivity may come as a surprise, but it's very important for being able to mix static and dynamic code on either side of any boundary. Now, in a sound gradual type system, we would insert runtime checks to ensure that each of these types are as annotated. And so this annotation would have actually introduced new errors to the program. In an unsound gradual type system, we may not introduce those runtime checks, but the type is still wrong, so your tool is going to give you incorrect errors and incorrect suggestions when we talk about the type of X. So these are the three properties that matter for automatic type migration. Safety, which is critical for having the correct types. Compatibility, which is necessary if you can't access all of the code that's going to be using the migrated code. And precision is so that we get good documentation and good types. That's the goal of our tool. So we present our approach, TypeWhich, which does produce safe migrations, but it allows the user to choose between precise and compatible migrations. So we acknowledge that sometimes you need compatibility if you can't touch all of the code that this code is going to be used in. And when we don't need compatibility, we still want precision because we want to get the best types we can. So we use syntax-directed constraint generation. Consider application. If f has type alpha and x has type beta, then the application will have type t. We can have a constraint similar to Hindley-Milner. We can have a constraint when f is any. In gradual typing, we have to consider that case, in which case the argument should also be any and the result will also be any. We also have to consider the case in which the result of the application is not any, but we want any in this context. In this case, we want to coerce to any, but we also need to assert that this gamma is ground, meaning when we coerce to any, a sound gradual type system will insert a number of deferred runtime checks. Because we can't see every context in which this value will be used, we can't make any guarantees about the type, and we can't guarantee those runtime checks will succeed. So a ground type is one for which all of these runtime checks will certainly succeed. For another form, we have abstraction. If x has type alpha and e has type t, then function x with type alpha, e, the function will have type beta. This, again, we can look at something similar to Hindley-Milner, but we also need to consider when we coerce the function to any. Again, we're going to assert that it's ground, so the expression and the argument are going to be any, and the ultimate result will also be any. In general, every expression can be typed as any, so this ensures that constraint solving does not fail. So in terms of performing the migration, we generate these constraints. We encode the GTLC types as Z3 data types. We also assert a soft constraint so that we prefer forms with less syntactic coercions. Our objective is to minimize the number of syntactic coercions which may not correspond to the number of runtime coercions. The result is a model that holds safe and more precise types. They're not necessarily the most precise safe types because that problem is undecidable, but they are more precise. We have an optional phase 2. So if we run phase 1 on an expression, we might get some type back, like int arrow int. Now, this is not compatible with all contexts. For example, it might be applied to a Boolean. So we ought to set the negative position, the argument, to any. Here's an example of a program where this is correct. A constant function that returns an integer might have type any arrow int because the result is always int. However, consider this other case in which any arrow int is incorrect, the identity function. The result type is going to match the input type, so the result should also be any. You'll notice that the only way to tell the difference between these two cases is to look at the expression again. So what we do is we add new constraints to the solver, and we rerun maxSMT, which may change annotations and change the final type. There are other ways that we could look at compatibility. We don't have to assert that every negative position is any. For example, we could allow arrow types in negative position. This allows us to have more fine-grained control between compatibility and precision, and there are other constraints that we could set to be in different levels of trade-off. We now present our comprehensive evaluation of gradual type migration tools. For our evaluation, we look at a number of type migration tools and a number of benchmarks. We re-implement 2 of the migration tools, one of which was lost with Flash. We also use 12 existing GTLC migration benchmarks, 10 new migration benchmarks that we created to challenge R and other tools, and 11 Grift benchmarks. We want to ask, how do each of these tools do on each of these benchmarks in terms of our 3 axes of safety, compatibility, and precision? To run our GTLC benchmarks on the tools, we give each tool all 22 GTLC benchmarks, and first ask if a migration is produced. Some tools don't produce a migration for every program. Of the remaining subset, we ask whether the migration is safe. Of those safe migrations, we ask two questions. One, is it compatible with every context? Two, how many types were improved? You'll note that TypeWhich in compatible mode produces entirely compatible migrations, as does Rastogi. Also note that TypeWhich in precise mode improves many more types, but does so at the expense of producing some incompatible migrations. We also evaluate our tool on the Grift benchmarks from Schmidt et al. Grift is a language like the GTLC, but with a bunch of reasonable language features. There are 11 benchmarks with 2 versions each, one with no annotations and one with complete human annotations. On 9 of 11 of these benchmarks, TypeWhich recovers all the human written type annotations. On another benchmark, TypeWhich recovers all reachable human written type annotations. In conclusion, we look at safety, compatibility, and precision as the 3 properties that matter for automatic gradual type migration. We present the TypeWhich approach, which is safe, but gives a choice between compatibility and precision. And we present our evaluation methodology for comparing these algorithms. We also present 2 new implementations of prior algorithms, a unified benchmarking framework that could be extended with more tools or more benchmarks, and all of our code and data is open source and can be found here. Thank you for listening to our presentation. We'll look forward to answering any questions.